How are you, everybody who is watching this video? I would like to take this opportunity to welcome you into one of the fundamental skills that I like to teach electronics engineering students and other related fields. And this concept is actual, how can you design a digital electronic circuit, whether used in electronics for the electronics purpose or some are in other fields, or used in electronics communication system. What are the steps that you have to follow? What should you think first, and then what should you think next? Okay, if this is the first time to meet me, my name is Olenjolai. I'm going to lecture you, or I'm going to teach you about the practical information concerning about digital electronics communication circuit. I have some physical engineering students in this class, and I would like to tell you that just the requirements for this course: fresh mindset, concentrate, ask questions, and then receive this good news and actualities, a foundation or fundamental news that you may apply whenever you are discussing about digital circuits. In previous workshop, we have discussed a lot about analog communication circuits or analog circuits. But this is the time now we'd like to try our level best to make sure that we teach you what we know about simple digital electronics circuit. How are you, students? How are you? Okay, welcome into the module called the Electronics Communication Lab. This is just a module to give us some contents, but the contents we are going to cover, it's not limited for the modules. These contents are for almost are very important in different electronics field and also in different related fields. So let us start with a quick review of the previous workshop, which is actually we call it workshop 1 with regard of with regards of digital electronic circuit. In workshop 1, actually we covered 3 concepts. The first one we covered about guided digital communication system, and the second concept, so we just see guided, or we call it wired digital communication system. Okay, and we define what is it, but also we drew the general block diagrams. Then I left that responsibility for you to go and learn and read about each block diagram. Then the next concept that I taught you about unguided, but however that we call it oftenly wireless digital communication system. Digital communication system. And then we discussed, so I taught you about the introductions about the digital circuits. That's another concept, digital circuits, where we say that we have 2 digital circuits. The first one we call it combinational logic circuit, And the second one, we call it a sequential logic circuit. So sequential logic circuits. And then we discussed about the general block diagrams of each. And then we ended that class. But also I gave you examples of sequential logic gates, where we say that we have SR flip-flop, T flip-flop, D flip-flop, we have counters, we have timers, okay? We have registers also, because we call them, we call them registers. So we have a number of sequential circuits, or sequential logical circuits. And then I gave you 10 examples of combinational logic circuit. The first example, Zuena. The first example, Zuena has forgotten. The first example is half adder. Let us mention them in sequence. The second one is called the full adder. The third example of combinational logic circuits is called the half subtractor. And then the third example, the first example is called the fully subtractor. Then the next example is called the encoder. That's the example number 5. Example number 6 is called the decoder. Example number 7 is called the multiplexer. Example number 8 is called the multiplexer. Example number 10, number 9. Pardon? Comparator. Another example is what? Magnitude what? Comparators. So today, let us carry on with how we can design. So what are the steps that we have to follow on designing combination? In this module, we are going to discuss about how we can design and how we can design combinational logic communication circuits. That's what we are going to discuss in this module. So in this module, we are going to discuss about combinational. So we are not going to discuss sequential. So sequential, there's another module that's called the digital electronics. You learn sequential, you'll enjoy. And I like that most because it's been taught by my previous teacher called the Madam Margaret Kabadi. And she has been actually trying her level best to entertain students by giving them different tasks to measure their level of thinking. Okay, so let us discuss about design or designing or construction, designing or construction or constructions of of digital circuits in general, not just for the communication. Designing or constructions of digital circuit. Class A, designing or constructions of digital circuits. Digital electronics, we forgot the very important word. Digital electronics circuits. So what are the important information? We say that so you say that in order to design or implement, okay, a digital electronics circuit, we say that there are some steps that must be followed to achieve the design. So it's just like in analog, in designing or constructing analog circuits, we need to follow some steps in order to make sure that we design that analog electronic circuits. Similar in digital electronics, we also need to follow some steps, but they're a little bit different from what we've been learning in analog. Okay? So we say that these steps are used it to design. I used it to design. Okay. I used it to design and analyze. I used it to design the digital electronics circuits. Okay. And when they are reversed, they are used to analyze the digital electronics circuits. So in electronics, we have four main functions. The first one, design. The second one, implementation. The third one is actual troubleshooting or analyzing. No, before troubleshooting, analyzing the electronic system. But the fourth one is troubleshooting in case that the systems have suffered some unexpected problems. So this is steps. So it's just like in case of analog, if you do remember that, we have some commons. What I've taught you what I've told you in electronics product fabrications or in designing analog circuits, actually I taught you the common steps that you have to follow. But in case of the digital electronic circuits, we have also some special steps regards with the digital electronics components. Because the digital electronics components actually have different operation principles compared to the power electronics components and compared to the analog electronics components. Are we together? Yeah. So if we reverse this step, we analyze. So if we reverse these steps, we analyze. So it means we can use the same steps to analyze the digital electronic circuits. Because, listen, in case of the designing, you have to start from idea or from the problem to solution. This is in case of design. And then in case of analyzing, you have to reverse. You have to start from solution of the problem to the problem. So this is what we call the analysis of electronics system. Your mobile phones, when you send to the mobile technician, actually don't expect that your mobile technician, so the mobile technician is going to design a new mobile phone. It's going actually to analyze which part has failed. Are we together? Are we together? But for instance, in this class, we don't have electric fan, so then you have to sync. So the fan is not there, we are feeling hot, that's the problem. How can you solve it? So he said that the following are the 5 steps that are followed to design the combinational logic circuit. The first step in case of the digital, it's very important for you to identify the number of inputs and the number of outputs. So first step, say first step, say first step, identify the number of the inputs and the number of the outputs. Identify the number of inputs and outputs of the digital circuits. Digital circuits. So this is even in case of what? I just took combinational because I discussed about combinational. But you may use these steps also when you're designing sequential logic circuit. So the first step, we have to identify, or you have to identify the number of the inputs and the number of the outputs of the digital circuit that you wanted to design. How many inputs do you have? How many outputs do you need? That's the first question. Why should we think about the number of inputs and the number of outputs of the digital circuits? This is the reason. Go with your bag. Why are you leaving your bag? So you have to start the outside. Okay. Then, we say that why should you think about the number of inputs and the number of outputs? Where are you going? You have to stand there at the entrance door. Are you going far? Okay. So this is the reason. For instance, for example, in your design, you will come up and say that I need to use the AND gate. For the AND gate, we have two AND gates. There's the AND gate, which is actual provides only two inputs. So input A, input B, pardon? How many are you? 2. No, until you reach 10. So keep finding the others. So this is input A, and this is input E. This is input A, input B. So this is the AND gate. So example, you can have a two inputs AND gate. Shukuru. So check who is not present and then call them until you are full. So check the class. Who is not present and call them. When you reach 10, you get in. With your neighbor, with your assistant, lady. So example, 2 inputs AND gate and 3 inputs AND gate. Okay, you ask the permission, get in. Shukuru, get in. And you get in, you just told me that you'll be late for some quiet time. Okay, so we can have the AND gate which has 2 inputs and single output. But also, in digital electronics, we have the AND gate which has 3 inputs. Okay, this is input A, input B, input C. So this is inputs and this is IoT outputs. So that's why you have to identify the number of inputs first and the number of outputs. Why? Because once you identify, you'll have a good selection of the particular digital electronics components that you'll need to use in your design. Wait until you reach 5, you will get it. So one of the important steps in designing digital circuits, you have to make sure that you identify the number of inputs and outputs in your digital electronics circuit. Okay, so let me just write some simple. Why do we need to identify the number of inputs and output? We say that first of all, we have to think. We have to think about the inputs and the outputs. You have to think about the inputs and the outputs of the digital circuit. Why? Because that you require to design or to implement by considering which type of logic operation, because the digital electronic circuits will perform different logical operation. By considering which type of logical operation will it perform. So this is the first step that you have to think, or you have to take consideration before you dive to the second step. So what will be the guidance? Actually, remember that the key is the problem that you want to solve. So remember that for this case, it's just I'm discussing about a six step, because you have to identify the problem, you have to propose the solution, you have to draw the general block diagrams. I think you remember those steps. And then after you draw the block diagram, you have to draw the detailed block diagram. You have to draw and then after having the detailed block diagrams, you should design, or you should implement. Should implement in order to, I said until you reach 5. So keep on calling others who are late. When you reach 5, you'll get in. So you can identify yourself, how many latecomers do we have in this class? That's the goal. Okay. So remember that the part we are discussing, remember that I taught you in some previous workshop that the first step that you want, first of all, you have to identify problems. Is this in the class? Next, you have to do what? To propose solution. Do you remember? Then next, you have to draw what? General block diagram. Right? And then next, you have to draw what? Detailed block diagram. And then to move, Johan, to move from detailed block diagram to the schematic circuit diagram, at this point, we have to do something, we call it design or implementation. Okay? Okay? So I skipped all of this steps because I have taught you how can you identify the problem, how can you propose the solution, how can you draw the general block diagram, how can you draw the the detailed block diagram. Then I'm discussing this part from the detailed block diagrams to the schematic circuit diagram, but for this case we call it schematic logical circuit diagram, because I told you that we have two types of schematic circuit diagram in electronics. We have schematic analog circuit diagram and schematic digital or logical circuit diagram. So in case that in your designs you need to use a digital system, then you have to think about the following concept when you think about design or implementing or constructing. Are we together? Okay. So these are the 5 steps within the one huge step that called design. And finally, what do we expect? Once you follow this step, finally you'll come up with the schematic logic circuit diagram. And once you have it, you go for the next step. You can simulate now, because you are very expert in simulation. And simulating is something that you don't understand. You don't have the theory behind. Johanna, go to your work. You see that now the duster is not cleaning clearly. This is somehow okay. Ask Ishkuru. Teach Ishkuru how to clean it. Then the second step of designing digital electronic circuit is create the truth table. Create the truth table of your digital truth table of your digital electronics circuit. Very important. When we've been discussing about data sheets, which is you say that it's out, it means it's okay. Let me ignore about what you have said. When you're discussing about the truth table, one of the part that you have to read and understand in the data sheets is just a truth table. But those we call them practical truth table. So the second step, you have to create the truth table of your digital electronic circuit. When I'm teaching you these 5 steps, we are going to use them to design one electronics digital circuit today. So you have to listen carefully, because we are going to learn and apply today this information. So create a truth table of your design. Class A, create a truth table of your digital electronic circuit. Say it loudly. No. Say it loudly. Say, create a truth table of your digital electronic circuit. Ladies, say yourself. Forget about the gentlemen. 1, 2, 3, go. That's the voice of more than 40 ladies in this class. Okay, gentlemen. 1, 2, 3. Let us go. Okay. Let us keep on. So in this step, we have to create the truth table. Leave me. The truth table for our digital Joanna electronics circuit based on the possible combination of inputs Alquino and the outputs. How many are you? You don't answer, eh? 4, get in. Claim your friends who is a late comer like you. Did you claim them? Abdullah, sit there, nearby Angelina. Where is the exercise book? You have it? Yes. Okay, put on the table and take your pen and write. Okay, so he said that we have to create a truth table for our digital electronic circuits based on the possible combinations of binary inputs. Binary inputs and the binary outputs. So you have to create the columns of the input, the columns of the inputs, the columns, then you have to create the columns of the intermediate, the columns of intermediate, or the columns of intermediate, and the columns of outputs. So when we drawing the truth table, I will show you where the columns of the inputs, where the columns of the intermediates, and where the columns of the outputs. So it's just a matter of thinking in relationship of the particular problem that you want to solve. Is it clear, student? Did you understand the second step? In case you have a question, ask it. Or if you didn't understand, let me know. If you remain quiet, I will assume that you have understood. Is it clear or it's not clear? Today, it's clear. Eh? Can you imagine about your friends, including Shane? Ask him, did you hear the question? Okay, they said this thing. So if it's clear, let us go. They said this thing. The steady state, once you have created the truth table, then we say that deduce the Boolean, Matatu, count until you reach 5, you'll get in. So Boolean, so deduce, I didn't say get in. Once you reach 5, latecomers, you'll get in. So check who is not there and call him or her. Hello, where are you? I'm waiting you for the entrance. I said the 5. Get out. Are you 5? So deduce the Boolean expression of the deduce the Boolean expression of the deduce the Boolean expression of the logical function, logical functions of the design by using either ones or zeros. So once we have a truth table for our design of our digital electronic circuit, Christina, where are you writing? On the exercise book. Why should you not turn off the computer? Are you doing something else? He'll never tell me. So, we say once you have the truth table, the next is say, we have to deduce the Boolean expression. Say Boolean expression. Boolean. Say Boolean expression. Boolean. Boolean expressions is the important phenomena in digital electronics. Get it? In digital electronics circuit more than you think. Because any digital circuits perform a particular Boolean expression. How are we going to deduce, or how we can deduce? Don't worry. You have connected into this workshop. I will teach you. Then the fourth step. Tell your neighbor we are in fourth step. Class, is it clear? So how do we deduce? We just see either make decisions. We are going to use ones in the output column or zeros in output column. So when you say 1 or zeros, we means about the binary inputs or the binary number, which means 1 and the 0. What do we expect in the truth table? Mostly in the truth table we expect to have ones, zeros, and we call it how do you call it the intermediate states, which is neither 1 nor 0? Where we used to represent by using X. Don't you care? This is not K-map. Undecided state. I taught you when I've been teaching about data sheet. But you forgot. You are very expert in forgetting. So we will see that, and these ones or zero, I think that yes, I have to add something here, ones or zeros in the output column. In the output column, because some other students they may use ones or zero of the input column. The first state, we say that simplify the Boolean expression, simplify the Boolean expression by using the Boolean algebra law or laws until it is in simplest form. Matatu, how many are you? Just like Matatu. Are you calling the others who are late like you? Call others. Just to check the class. Why are you hiding yourself? You may stand there at the entrance door. Come, all of you three, all the three students, come at the entrance door. Because today I want to teach you in different style. Come on, please. Check who is not there and who is you think that is a late comer. Just come and check. Don't enter. Just check and make a call. Hello? I am waiting you. I deleted it. Okay, don't worry. So, the fourth state. The fifth state. Fourth or fourth? Fourth state. I've written the fourth state. But you have understood, it's simple. The fourth state. The fourth state, and we say that, simplify. Matatu. Get in. The Boolean, but claim the latecomers like you. Get in, all of you. Go and call your colleagues. So simplify the Boolean expression by using the Boolean algebra, laws to its simplest form. Why do we need to simplify? Why do you use to simplify Boolean expressions in digital electronic system? The reason is we want to minimize the size of the digital electronic circuit. That's one of the reasons. But the second reason is also we want to minimize the cost. Because we may implement it or we may design a digital electronic circuits by using maybe 5 logic gates. While in case we simplify, we may reduce the number of logic gates and use 2 logic gates which will perform the same logical operation. Class, are we together? That's why in fundamental of digital electronics, you have learned about the Boolean expression. That's why that we have taught you about the Boolean algebra laws. We taught you in advanced electronic science, when you have been in A-level education, there's a particular subtopic that called the digital electronics, and you learned about almost 60 to 7 Boolean algebra laws. So that's the applications. We did not teach you those Boolean algebra law in order to use them to answer questions in the exam. No. Nation. Huh? We taught you in order to use them in designing the digital electronic circuits. Are we together? So we did not teach you in order to answer questions in the exam. Okay, one of the objectives, answer question in the exam. Then after answering the question of the exam, when you graduate, who will give you some questions again to answer in the exam? In life, we don't have school exams like the one we have at school. In life, is there any question that explain briefly? No. Mention? No. Describe? No. In life? Okay, I have a problem. What's the solution? Money. You don't have money, then wait the disaster. Then the fifth state. The fifth state, sometimes if you have gone through all the Boolean algebra laws that we have in digital electronics, because Booleans first it's the names of the first persons who have introduced the concepts of the binary number, who is George Boole. He was a French physicist. So it's the name of the person. That's why we don't write Boolean by using a lowercase. We start with a uppercase. So, if you have learned that, you have learned about Boolean algebra laws, especially in first year digital electronics modules, then you find out, or you have discovered, or you have heard, sometimes the Boolean algebra laws fail to simplify the given Boolean expression into its most simplest form. So for that case, then another physicist or another engineer, electronics engineer, who's called the Kenneth, gave the idea how to maneuver. So the physicist, we say that if the Boolean algebra law. If the Boolean algebra laws fail, say fail. Say fail. Patience, say fail yourself. A, to simplify the Boolean expression. The Boolean expression into its simplest form. Then Urasa then use the K-map. Okay, this we call just the KNAF. Or K-map. In short, we call it KNAF map, to simplify the Boolean expression into its simplest form. So as a digital electronics engineer or digital electronics technician, wait as the latecomers. When you reach 5, you'll get in. So check who is not in the class and call him. Tell him, I'm waiting for you to get into the class. So as a digital electronics technician or digital electronics engineer, you don't have an excuse that I failed to simplify the Boolean expression into its simplest form. When you say simplest form, it means you cannot simplify any further. So once the Boolean law fail, you have to go for the K-map. But remember that the K-map, or you may, sometimes it depends the design. In some of the designs, you may skip the 5th step, because if the Boolean law simplify the Boolean expressions, then you are done. Okay? So you can understand why have you been taught K-map once you came in your bachelor in electronics and telecommunication engineering. And I have a good news that you have been taught in fundamental of digital electronics. Okay? So we didn't teach you in order to answer questions in the exam. No, we taught you because that the fundamental skills you need in designing or implementing digital electronics circuit. Kevin, check who is not in and call him or her. Okay, then the 6th step, this will be the last step. We say that draw the schematic circuit or logical circuit diagrams. Once you reach 5, you'll get in. Otherwise, you won't get in. So check, Dixon is there. That's one of your friends. Christina is there, Mabeza. So draw the schematic logical circuit diagram of the most simplified Boolean expression. Abdullah, you are not writing. While you have exercise book, you have a pen. Right. Right. Check from Angelina Ozwena. Kevin, did you understand their condition? That is today's condition. Just a call, just a check. If you have, I want to know if you really have a social network with your colleagues, because the first thing you want to have the earphone number. For instance, Kevin, in this class, are you 81, 82? 82. Benjamin is not in this class. Benjamin Joseph. So call him. So I assisted you 1. So find the other 4. Okay. Then the 6th step, we say that draw the schematic logical circuit diagrams of the most simplified Boolean expression. Read it. 1, 2, 3. Let us go. 1, 2, 3. Read it again. Okay. How many are you? 1. Call Benjamin. If you don't call, you will remain there until the end of the class. Okay. So these are the common 6 steps that you have to think as a digital electronics engineer or as a digital electronics technician. So let us try to apply them in a particular with respect to this module and with respect to the examples. So then we say that now, ladies and gentlemen, 7 steps followed to design, or let's say that Precious, you are leaving. Come back. No, I said no. Designing or constructing. You are coming while you are going. Constructing. Don't come here. Just go back to your seat. Just go and sit for 5 seconds, then you'll go. Go and have a seat for 5 seconds, and then go. Okay, designing or constructing of what? Combinational logic circuit. So Kevin, make a call and give me feedback. Logic circuit. The other one who is not in this class, Kevin, I'm talking to you, is the other ones who is not in this class. Let me try to check. You are Sierra, Eliakim Matthias. So you see how dangerous you are. So he's talking with Benjamin now. Designing or constructing of combinational logic circuit. So he said that in designing of the following combinational logic circuit, following combinational logic circuits follow the same steps. For instance, if you want to design a half adder, if you want to design a full adder, we follow the same steps. If you want to design the full subtractor, we follow the same steps. And also if you want to design the but you didn't sit at your place. A half subtractor. A half subtractor. So we have some common steps, 7 steps. So the following combinational logic circuits, the designs of the following combinational follow the same steps, the same 7 steps. in designing a half adder, a full adder, and a full subtractor, and a half subtractor. So let us practice these 6 steps by designing one of the digital electronics circuits. Johanna? So now, design or construction or designing or construction of of half adder. Kevin, what did they say? Huh? Get it? Yes, I think that I have to mention this, but okay. Yes, let us just use them in designing there. So I say that whenever you think about designing a half adder, there are 7 steps that you have to follow. If you want to design a full adder, there are 7 steps that you have to follow. If you want to design a full subtractor, there are 7 steps that you have to follow. If you want to design a half subtractor, there are 7 steps that you have to follow. In case of other combinational logic circuits, you might find that you may have 7 or less than 7 or more than 7 steps. Robert, stand up. Okay. So first of all, we say that, what is a half adder? What is a half adder combinational circuit or combinational logic circuit? Because definitions is very important. So you say that a half adder, class A half adder. Say half adder. So you say that a half adder is a type of combinational logic circuit that adds only 2 bits or 2 binary inputs, 2 binary inputs to give the sum and the carry. So a half adder, this is the one type of combinational logic circuit. Where are you going? Sit down. Sit down. So a half adder, we say that this is the type of combinational logic circuit that adds only 2 binary inputs to give out or to give the sum and the carry. Class say half adder. Again, say half adder. Say half adder. What is it? It's amplifier. Is it what? A nation. What is it? Nation is nation is enjoying the hangover. Wash your hands. You'll wash at the end of the class. Okay, so we say that this is the types of combinational logic circuit which can add only 2 bits to give out the sum of those 2 bits and the carry. The half adder, one of the limitations of the half adder, cannot add more than 2 bits. That's one of the limitations of the half adder. And because in digital electronics, we have some situations where that we need to add more than 2 bits. But the half adder is limited. That's why the digital electronics engineer, they also designed the full adder. Because the full adder itself, it can add more than 2 bits, but itself also it can't add more than 3 bits. You have to understand the limitations, because as I taught you that half adder, mostly full adder, is used in logic arithmetic unit, and also is used in most of scientific calculator. Get it? So this is the simple definition of the half adder. So we expect it to have 2 outputs. One we call it the sum of the binary inputs, and the other ones we call it the carry. And to think about sum and carry, it's very simple. It's confusing some students in case of binary number, but we've been taught this concept when we've been in nursery school. So in nursery school, we have been taught that how we can add a decimal number 5 and number 4. So 5 plus 4, what do we get? 9. So 9, this is the sum, but the carry is 0. For this case, the carry is 0. Then we have taught that maybe to add 4 plus 6. 4 plus means that 3 plus 6. 3 plus 6 is equal to what? 9. Carry is 0. So sum is 9, carry is 0. Sum is 9 for this case, carry is 0. Then we've been taught to add 3 plus 5. What do we get? 3 plus 5? 8. So this is the sum and carry is 0. So the phenomenon of sum and carry is not new when you talk in respect of decimal number. It's a new concept in context of the binary number. Again, once we have graduated in the first year of nursery school, then we went to the second year, right? In second year, we've been taught to add the numbers which give us 2 digits. For instance, we've been taught the first number. I remember that I've been taught in 1991. 1991, when I was standard 1, I've taught my teacher. Taught me how to add 5 plus 5. I was surprised because I had the experience of getting a single digit. Right? So then, after graduating that, our teacher said, let us go to the additions that brings 2 digits. And then additions that brings 3 digits, etc., etc. Nowadays, you might think that these are the simple mathematics. But by that time, you know. How many sticks did you enjoy at home? When your mother or your father give you a simple, simple mathematics, and you think about playing. 5 plus 5? 10. So 10, we write 0, and then we carry 1. So this one that we carry, it's the one that we use right here. Then, I remember that my teacher taught me to take 5 plus 6. I got 11, or we get 11. We just use write 1 and carry, it's 1. But that carry, we carry over. So we carry over, that's why I write 11. Okay? So it's just nothing. Then I've been taught, later on, I've been taught that maybe 3, 9, 4, 8, plus 40, plus 4, 9, 7, 8. 8 plus 8? 8 plus 8? 16. I write 6. The sum is 6, he carries 1. Shukuru. Then 4 plus 7? 11. So 11. So the sum is 1. Then plus this carry 1. Makes what? 12. So the sum is 2, carry 1. Then 9 plus 9. What do we get? 18. We carry the 1 from this addition. So 18 plus 1, 19. So the sum is 9, carries 1. Okay? Okay? So don't think that the concept of sum and carry, it's new. No. It's new in context of binary number. But in context of decimal, we are expert on that. Similarly, in case of the OT, the difference and what? In case of subtractor, difference and what? Difference and the borrow. The same concept. Then 3 plus 4, 7. We carry the 1. 7 plus 1, 8. Then we ended our addition process for the decimal number. So similarly for the binary number, if you have 0 plus 1, the answer is what? 1. If you have 0 plus 0, the answer is what? 0. So the maximum binary number is 1. It's just like the maximum decimal number is 9. Christina Mabeza, come please to the class. What did I say? Let me repeat. For the binary number, did you remember? Because this is not new. I just reminded you. Did you remember it? Is it clear? No need to write, yeah? Okay. These are the simple stuff. For the binary number, the smallest binary number is 0. The largest binary number is 1. The smallest decimal number is 0. The largest decimal number is 9. The smallest octal number is 0. The largest octal number is 7. The smallest hexadecimal number is 0. The largest hexadecimal number is F. So whenever you are, hey, Urasa, stand up, stand up, stand up, stand up, stand up. You are sleeping, stand up. So whenever, it's just like in decimal. Whenever we add two numbers and then the sum exceeds 9, we have to carry. Similarly, in case of binary number, in case whenever we add the two numbers and the sum is 1 or greater than 1, we have to carry. In case of octal number, if you add the number and the sum is greater than 7, we have to carry. In case of hexadecimal number, if we add the two numbers and the sum is F, we have to carry. What kind of digital electronics you are learning? That is extremely fundamental digital electronics of binary number. You know how to convey it, eh? That's all. Okay. But adding, subtracting, multiplying, dividing, it's not yet covered yet. Okay. So I've just clarified the meaning of sum and carry in digital electronics. That was objective of the previous explanations or illustration. Okay? Let us continue our business of designing or constructing our alpha. The first step. The first step, we say that draw the general, let's say that the detail D, draw the detail D block diagram. Draw the detailed block diagram. That's the first step. Of, half, adder. We want to add the 2 bits. If you want to add 2 bits, the first block that we need the power supply unit to power our digital electronics components that will be constructed, will be used to construct the half adder. Then, okay, this system or this combinational logic key system, it will add 2 binary inputs. So for that case, those binary inputs should be generated by the input unit. The input binary unit. The input binary unit. Class A is the input binary unit. Very good. And then our brain or our control unit is what we call our half adder. So what the limitations of half adder? It can add only 2 binary input. Okay? So if that's the case, we expected that. Oh, let me just finish. Again, what are the outputs of the half adder? We expect to get the sum and to get the carry. And the sum will connect with another system. And the part of the carry will connect with another system. So this will be the block of the sum of the 2 binary input. And this the block of 40 of carry. How many blocks do you have? Simply, this is the power supply unit block. This is input binary units block. This is output unit block. This is the control unit block. As I told you that. I told you about the 4 general or the 4 common block diagrams in any electronic system. So stop writing. Then the power supply, first of all, should be used to power the half adder. And this one we have to specify. It should be the C power supply. Why? Because there is no any digital electronics components that operate with AC power. Listen and look. Then the input binary units, it depends. It may be actually, it's a divest. In most cases, it can be a digital sensor. So if it's a digital sensor, then it will need the DC power supply. Abdullah, look. Then once this input binary unit should be actual that feed the inputs to the half adder. This will be the first bit will be passing here. The second bit will be passing here. I said stop writing and stop drawing. Then once we add these 2 binary inputs, then we expect it to get the sum, but also we expect it to get the carry. Then that's all. This is figure 1. Figure 1, the general, the detailed block diagram of the half adder. Class, is it clear? Is it clear? Okay. Then that's the end of the first step. We can go for the second step. Go back to the steps. The second step is what? Go back to the 6 steps of designing a digital electronic circuit. Baraka, read for us the second step. Read the second step that I have taught you. The first step is actual Identify the number of inputs and what? Outputs. So for our case, the number of inputs are 2. We have 2 inputs and you have 2 outputs. Okay? Okay? So from this one, we say that, okay, the number of inputs is 2. Then the number of outputs of the half adder is 2. Because I was expecting some serious students to ask me the question. But sir, in the steps that you've taught us, the first one, you taught us to identify the number of inputs and the outputs. But there you draw the block diagrams. What is happening, sir? Did you confuse? But I have students who are waiting to copy. They are waiting to copy. Okay, copy. Tell me the second step. Create the truth. The truth what? Say it again. Say truth table. Truth tables are always created depending on the requirement. I know that you have claimed the truth table of AND gate, of OR gate, of NOT gate. Those are the really situation. First of all, those are the really situation. And they have been created based on the particular digital electronics component. So even yourself, you have a permissions to create your own truth table according to the design that you want to make. Are we together? Are we together? Yes. So the second step, we say that, create what? The truth table. The truth table of half adder. So how many binary inputs do you have in a half adder? Two. So we expect you to have 2 conditions. What are the possible combinations in those 2 conditions? We have 4 possible combinations. The first one, if the 2 conditions did not take place. The second one, if one or if the first 2 conditions has taken place while the second ones did not take place. The third combination is just a probability. It's just the issue of combination. Okay? Then the third one, if the first 2 conditions did not take place, but the second conditions has taken place. And then the fourth combination, if all the 2 conditions have taken place. That's how we create the truth table of the 2 binary inputs. Should I repeat? Is it clear? I have to repeat. We can have this condition that Angelina attends the class of electronics workshop if Namvua attend. These are the 2 conditions, simple 2 conditions which are simple. And it's very simple for you to remember and keep them. Angelina and Namvua are kind of friends. So because they are friends, sometimes their attendance or performance of something depend on the presence of the other one. I just took an example. You can write yourself and your other best friend. So there, it's not necessary to write Angelina. You can write Mvunye and what? Alawi. Huh? Yes. Mbunye and the... okay. Let me continue. Okay. So, this is the first sentence. Angelina attends the classes of electronics, electronics communication laboratory. E40, Namvua attends. So how many sentences do you have there? But they are conditional sentences. Okay? So you wanted to add the the binary inputs called the Angelina and the another binary inputs called the Namvua. So what are the results that we expect from two sentences? It's simple. The first results are, it's possible that, or we say that, so Angelina attends the class of electronics communication laboratory if Namvua attends. So the first possible combination, Angelina and Namvua, or Namvua did not attend the class, so that she led Angelina not to attend the class. It means both of them did not attend the class. That the possible combinations results. Right? The second is this one. Angelina attended the class, but Namvua did not attend. Okay? Okay? The third one, Angelina did not attend the class, but Namvua attended the class. And the fourth one, and both Angelina and Namvua attended the class, just like today. So how many possible combinations? 4. That's why we say that in order for you to create the columns of the binary inputs, this is the formula. So you say that the binary inputs of combinational logic circuits, the binary inputs, we create them by using this formula, 2 power n, whereby n is equal to number of 40 binary inputs. So this is, this is possible combination, sorry. This is possible combination. Possible combination. And we told you the concepts of permutation in probability and the combination probability. That's one of the applications. But for you, you use them to answer the Form 4 exam and the Form 6 exam, and then tell them combination and permutation, bye-bye. My dear students, I want to tell you that in real life of electronics engineering, you have to remember what you have been taught from home, nursery, primary, O-level school, A-level school, first degree, second degree, third degree, and even publications or research that you'll make to become a professor. So you have to remember all of them. So in case of this case, let's say that the possible combination, that's what we say, the possible combination of binary inputs of 40 of half adder. We expect you to have half adder. We expect to have how many inputs? 2. So it is 2. What the number of the inputs in half adder? 2. Right? Zuena Masebo, 2 power 2 is equal to what? 4. So expect it to have 4 possible combinations. If you're designing a digital circuit whereby the binary inputs are 5, Christina Mabeza, tell us the possible combinations. How many possible combinations will you have? 2. Started. Why? Because 2 power 5. Abdullah, clap your hand for Mabeza. She was not in the class. Again, clap. Ongera. Yes, that is Engineer Abdullah. A very interesting student in this class. So, you should not be limited. That's why the first step, identify the number 40 inputs and what? outputs. If you don't know, you will fail in the second step of creating the truth table. Are we together? Are we together? Are we together? Yes. Okay, fine. Thank you if you have understood. So when you say about the possible combination, remember that these possible combinations represent things by using binary number, right? Not this one, because we have a modern age students. The possible combination are represented by using binary number. So then our truth table is this one. Stop writing, stop drawing. Look on the blackboard and listen. This is our truth table. Try your level best to draw a neat truth table. So at this point, we have input. And then at this point, we have output. We say that you have to create the columns for the input and the columns for the output. For this case, we have one column for the output, one and two columns for the input. So this one, let us call Angelina attend the class of electronics communication laboratory. Let us use the notations of A. That's why we taught you mathematics and the special algebra. Let the age of Musa to be X. And let the age of Zuena to be Y. You forgot those simple mathematics. They are a little bit challenging in primary school. I remember them. Maswali ya umri. Nifaa umesahau. You like the mathematics of what? Of account. Ankara. Unahesabu na zero ankara. Nzuri sana zile. Si ndiyo? Aya. And this one, so the possible combination I forgot. The possible combination here, we are going to have also two columns. One is called the sum, and the other is called the what? Carry. So look. Look. Stop writing, please. So you have four possible combinations. That's why we have a truth table of the four possible combinations, right? The first one we said Angelina and Namvua did not attend the class of electronics communication laboratory. So if Angelina did not attend, we can say that we represent that situation by 0. And if 40 also Namvua did not attend, we represent that situation by using 0. But it's not constant. It means that it's not a guarantee. You may make decision that if Angelina did not attend the class, you represent by 1. And also if Namvua did not attend the class, represented by 1. That's okay. Should not claim. Then the next combinations we say that Angelina attend the class. Remember, A is Angelina, B is Namvua. So Angelina attend the class. But just to remind you, let us use this is N, Namvua. So Angelina did not attend the class. Angelina attended the class, right? At the same time, Namvua did not attend. Then Angelina attended the class, but Namvua, Angela did not attend the class, but Namvua attended the class. And then, but today, we say that Angelina attended the class and Namvua attended the class. This is also possible combination. I know for you, you crammed from bottom to top. Get transformed from today. There's no need for you to cram that you should start with 0, 0, 0, 1, 1, 0, or you should start with 0, 0, 1, 1, and 0, 1, no. You used it to do so when you have been a kid in digital electronics. Now, you are becoming an intermediate electronics engineering student. Are we together? Get what is going on? So I know for you, you are expert to reverse this. Even if you reverse, it's fine. But try your level best to make sure that you alternate them. Because sometimes in exam, we give you some questions which actually they don't have the proper or the normal arrangement that you used to experience. Today, Dominic is writing. Today, Dominic is what? Writing. This is the serious class. So then now, let us go to the additions of binary number. Right? 1 plus 1. 1 plus 1 is similar to what? 9 plus 1. 9 plus 1 is equal to what? 10. So use right is 0, we carry 1. So in case of digital electronics, 1 plus 1, this representing what? Is similar to, it means that we'll carry 0, we'll have a sum of 0 and carry 1. Why? The simple meaning is the mathematics that have been given by my teacher when I was in standard 1. 5 plus 5, this is what? 10. We write 0, we carry what? 1. Right? Okay. Then, so if that's the case, you say that, so it is what? It is 0. 0, we carry 1. Don't claim, please. Tell your neighbor, don't claim those stuff. Tell your neighbor, don't claim those simple stuffs. Your neighbor is against them. Tell her again, shake his head or her head. Don't claim these simple steps. Touch the head of your neighbor as a sign of blessing. Emmanuel, you have 2 neighbors. Some of you are touching the heads of your wirelessly. Then 0 plus 1 is just like you have 4 plus 5 in decimal number. 4 plus 5. 4 plus 5. 9. So there's no carry. So the answer is 9. Carry what? 0. Similarly, 0 plus 1, the sum is 1. Carry is 0. But for you, you are claiming the whole night. Sum carry. 1 plus 1, 0 carry 1. 1 plus 1 0 carry what? 1. Then you find in exam 1 plus 1 plus 1 plus 1 plus 1. Then you say this is the tough. No, it's not it tough. Then 1 plus 0. Is just like what? 4 plus 4 plus 4 is equal to what? 8. Carry what? 0. Simple like that. You free your brain from cramming. Because you overdose, you utilize, you abuse your memory by just cramming this simple stuff. These are very simple. So the sum is 1, carry what? 0. Right? Mickey Daddy, 4 plus or 4 plus negative 4. Mickey Daddy is equal to what? 0. Then you carry what? 0. So 0 plus 0, mvunye. Say loudly. 0. Then we carry what? 0. So this is our truth table. Remember that for them, so we used to label them at the top. Table 1, the truth table. The truth table. The table, this the standard notations. We label them on top, not at the bottoms like the figure. Remember that any table or any figure which is not labeled or which is not named is meaningless. Because I remember that in the test 1, I gave you a number of diagrams to draw, but you don't name your diagram. First of all, you don't understand the diagrams you drew, And then if I say, okay, let me try the name, just try to mark the name, then even the name is not there. The truth table of half other. Class, is it clear? Go back. What the second step? Your neighbor is drawing the truth table by using a pen. You see your neighbor? How is she or he serious with electronics? And what the next step? Pardon? I just hear the voice of ladies. What the next step? What the third step? All the students, what the third step? So how many outputs do you have? 4. How many columns of outputs do you have? 2. So for this for the third step, we are going to have 2 Boolean expressions. 2 Boolean expression. But you didn't finish that sentence. Deduce the Boolean expression from what? The truth table by using what? Ones or zeros. So in this column we have zeros. This is 0 and 0. We may use either 0 and 0 or 1 and 1. In this column we may use what? We have 0. We may use these 3 zeros, or we may use 1. Okay? Okay? So the set is saying from an A, we say that let us deduce the Boolean expression of the sum. And then let us make decision by using, many students are good to work with ones. By using what? Ones. Why? Because many students, they like to use sum of product rather than product of sum. Which your AKA, according to what you have claimed, the SOP and the POS. SOP, it's what? Sum of what? Product. And that one, the other one, POS, it is what? Vice versa. Product of what? Of sum. Life is tough. So how many ones do you have in this column of sum? Stop writing. Emilianus, how many ones do you have in these columns of sum? 2. Where are they? This one and this one. So then, what are the name of these Boolean expressions? It's the output is sum. So we are going to use these ones. I say stop writing, stop drawing, look and listen. So we are going to use this. This one is found when Angelina attended the class of Electronics Communication Laboratory, but Namvua did not attend. So if Angelina attended the class, we may represent this one, it depends. The usual notations, we may represent these ones as A complement and this one as N or as B. Remember that you may use A as a B or you may use N, because some students that are expert in working with A, B, C, D rather than what? N, P, Q, R. So for that case, you say that the sum for this case, so Angelina attended class, but represented by complement. And A, so we have the AND gate, and A, Namvua did not attend the class. Or in other words, you can say that A bar or NOT gate of A and A B. Okay? A. So we are going to use, when you use ones, it means that you are going to use a sum of product. So this is the product. So products, you use the AND gate. And then you have to find a summation. Then we have the other one. The other one, we say that Angelina did not attend the class, and while Namvua attended the class. So NA and ba. In other words, this is A and A, B, ba. So it's just you who have to decide that if either Angelina or Namvua attends, let's call it 0. And if they don't attend, according to what we have said, let us call it 1. You may reverse. It's fine. I did not say that let us call attends 1 and not attend 0, because you are expert on that. I want to teach you the new concept, how you can think. That's why that in previous workshop, I told you that the binary bit 1 may represent 0 volt or 5 volt. And the binary 0, the binary number the binary number 0 may represent either 0 volt or 5 volt. Right? To extend your understanding. You have been expert on what? Using 1 as the, it means that the 1 represents 5 volt and 0 represents what? 0 volt. Class, is it clear? Class, is it clear? Should you use this notation or the ones we have in brackets? In brackets, eh? Okay, fine. So you have A bar and A B. A bar and A, or remember that this is AND gate, this is NOT gate, AND gate, OR gate, AND gate. But B, we have a NOT gate. So this is our Boolean expressions for the sum. I said stop writing, listen. How many logic gates do we have here if you want to implement this Boolean expression? Quickly. Nation, stand up, go and dress yourself outside. How many logic gates do you have there if you want to implement that Boolean expression? A? 3. Okay, some say 3. Shukuru? 5. So Shukuru said we have 5 logic gates. Nation? How many logic gates do you have there? I said go and dress yourself, please. The situation is not friendly user. Oro, how many gates, logic gates do you have there? 3. We can implement that Boolean expressions by using 3 according to Oro and the Angelina. Abdullah, tell us, how many logic gates can you use there to implement?
5.
5. So Abdullah said 5. Toba Elias, tell us. 3. Then now, Dixon. Matcha. Tell us, how many logic gates can you use to implement that Boolean expression? We can use 3 or 2. Get to. Tell us, how many logic gates are we going to use to implement? Get to. First of all, clap the hands. Get to, go and dress yourself. Go out. Go out. Winfrida, how many? 3. Precious. How many logic gates can we use to implement? 1. Okay. Jessica, some of the students are praying for me not to see them. Get to, go out. Quickly. Amedeo? 3 logic gates. Okay. So in case you want to implement this, okay, I think that let me just answer the question by drawing, because it's a contradiction. Some say 1, some say 3, some say 5. Some say 4. Kankesha said 4. That is Kankesha. Kankesha. Kankesha, who Sonia is talking to Kankesha. Okay. So this is not a part of the design. I just want to give you the correct response. It's not a part of the design. I just want to show you why should you simplify. Because the next step, the first step, we have to simplify that one. Okay? So why? If you wanted to implement that Boolean expression, we are going to use this kind of logic gates. So this is A, this is B. So if that's the case, we have A, B. Then you have A. So you have A. So you'll have A. Then we are going to have another and the gate. Because the door represents the AND gate. And then this one, we say we just need the B. B NOT gate. But you have a NOT gate at B. And then these outputs are combined in OR gate. So this is, we call it sum. So this is input A or input B, or we call it Angelina and the NAM4. So how many logic gates are there? How many logic gates are there? 5 or 3? Or 4? 3. 1, 2, 3, 4, 5. I didn't ask that what are the logic gates used to implement that circuit. Listen the question. I asked you the number of logic gates have been used. Because for what you are confusing, this is NOT gate and this is not, but these are the two NOT gate. And these are the two AND gate. The challenge, you are learning this concept more theoretically rather than practically. Okay, so if you say that we ignore other next steps, we have to, this is the one, so you'll find them in one integrated circuit, this NOT gate and this NOT gate, because you have EXA or EXA inverter NOT gate, and you'll have another integrated circuit, that including 2 AND gates. However, this self, it has 4 AND gates, and you'll have another integrated circuit, which actually contain 4 OR gates, but we'll be using 1. So in order to implement the half adder by using this logical or schematic circuit diagram, in case of the sum itself, you are going to use 3 integrated circuits. Creamers, go and dress yourself. So this is, it's not a part of our design, but just we want to show you the challenge. Why do we need some other steps? Because this one will occupy a very large space of your circuit. Secondly, it's expensive because you'll be using 3 integrated circuits to construct a half adder that will provide you the sum of the 2 binary inputs. It's expensive, it occupies a very large space, which is not economical in electronics. Are we together, class? Are we together? Are we together? Just to number to remind you, this is number 1, this is number 2, this is number 3, this is number 4, this is number 5. So those who have said 3, they have the response. Those who have said 4, they have the response. Those who have said 5, they have the response. Those who did not mention, they have the response. Okay, so we are done with Roman A, Roman B. Deduce the Boolean. Yuda, Simon, go out. Brace yourself. Boolean. Boolean expression of the carry. Carry of the half other. So we may either use 1 or zeros. Okay? How many zeros do we have? How many zeros do we have in the column of carry? 3 zeros, right? And how many ones do we have? 1. So it is simple for you to deduce the Boolean expressions by using the few number of the bits rather than by using the large number of the bits. Because you'll be using the large number of the bits, you have to perform some task of simplification. Right? That's all about design. Design is all about thinking. That's why I cannot understand you if I give an exam and you fail to think. Because you came here to learn how to think. Tell your neighbor, how many times did you learn how to think? What you have been learning, how to answer. Tell your neighbor, retire to learn how to answer and learn how to think. Tell your neighbor, please. So for this case, we need 5 logic gates to implement. Okay. So if that's the case, we are going to use what? By what? Using 1. Not once, because when you say once, it's plural. When you have this one, when you write this one, this means plural. So if you have just a singular, it's 1, like this one. Hey, Win, are you sending the signal? Win, who taught you to send the signal while I'm teaching? Okay, so by using what? 1. Somebody who has a phone number of Gertrude, call her, and Nashon, and Simon Yuda. So, carry. Carry is equal to what? So for carry, let us use 1. What are the possible combination? 1, 1. So simply, we say that A and B. This is simple. Rather than using A complement and B plus A and B complement plus A complement and B complement. Because you may use that once and you will deduce the same Boolean expression. So A and what? And B. And how many logic gates do you have here? 1. You have been preparing that response, You said, Olenjolai. You were unfair for the first question. But for this one, that's my size. Ask it, I will answer you. So you are going to use only 1. So if it's only 1, you should not bother to simplify it any further. It's enough. That's the smallest, it's the simplest form. But for you, you say that, you have to go to the next step, right? Simplify the carry expression. And then you write, it cannot be simplified. What the next state? A. Bundala. What the next state? Get to Simon Yuda. Nation. The first state. Simplify, Simplify what? The Boolean expression. So which one should you simplify between the two? A? Go out. Dennis, go out. So which one should you simplify? Go out. Which one should you simplify between the two? A, the Boolean expressions of what? Of sum. Why? Because carry is in simplest form. Are we together? A? So simplify the Boolean expressions of carry of half adder. How do you simplify? We have sum. We had A and the B complement plus A complement and the B complement. So if you refer the Boolean algebra laws, that simply we call it its exclusive OR. Okay, it's exclusive OR. So you say that to recall, we have taught you that A plus B, this is equal to A and A, B, or A complement and A, B. So now, in case of the sum, the simplified expression, Boolean expression, is this one, where we are going to use only one logic gate to implement the sum of the half adder. Joseph Pasco, you are not in the class. Physically, you are in the class, but in your mind, you are in Mbeya or Arusha. Or maybe you are thinking about Samuel Ringo, something that he has made to you last night. Are we together? So now we have simplified. Instead of using 5 logic gates, we will implement by using only 1 logic gate, which is economical. We are going to use only 1 integrated circuit, and I will show you how we implement it practically. So it's economical, and also it occupies a very small space. It's just like the motherboards of your smartphone. Are we together? A, the fifth step. A, if the Boolean algebra laws, A, Shane, read the fifth step. He's not there. Dixon, read the fifth step. Dixon is not in the class. Gaudens, read the fifth step. So the fifth step depends on the first step. If the Boolean algebra laws fail to simplify the Boolean expressions, then use what? K-map. So there's no need to use what? K-map. Why? Because both Boolean expressions are in their simplest form. So the fifth step, we say that skip it. Oh, no need of it. Then the sixth step, I'm asking you a question. Read the sixth step. You are just looking over me. How can I help you? 1, 2, 3. Read it loudly.
Draw the semantic logical circuit diagram of the most simplified Boolean expression.
Robert and Mugisha, stand up together and read the sixth step yourself. First of all, stand up and then read loudly. And Mugisha, stand up and read the sixth step. You see, they are not in the class. Read. We don't hear you. 1, 2, 3. Read loudly. We don't hear you. Okay. Thank you. Have your seat. So the sixth step. Now let us draw the schematic logic circuit diagram of the the schematic logic circuit diagrams of half adder. What are we going to use? By using the simplest form. Sum, we say it is A exclusive or B. And also the other ones, carry, we are going to use just what? A and B. Subtracting, subdrawing. Let us draw. So this is the schematic symbol of XOR gate. Let us draw it quickly. So here we're going to have sum. This is input A, this is input B. Then also we have what? The AND gate. Huh. So A, B. This is carry. So if we did not simplify the Boolean expressions, we could implement the half adder by using 6 logic gates. Because this is only for the sum. If you add the circuits for the carry, you'll have another 6 logic gate, which is AND gate. Are we together? So this is figure what? So remember that this is input. But remember that these are the inputs, these are the outputs. Remember that in this schematic circuit diagram, we did not show any connections of the power supply. And hence we did not discuss about the input unit. We did not discuss about the sum and the carry, that once we get the sum, what will it perform? Once we get the carry, what will it perform? We did not discuss, we just discussed only one block. What are the names of that block? The block that's called the half adder. Are we together, students? We had 5 blocks. In that schematic circuit diagrams, we did not show the block of power, DC power supply unit. We didn't show that the block of input. We just show the signal, which is the binary bit. We didn't show that the source, where does that signal come from, right? Also, we did not show that for the part, once we get the carry signal, then what can it perform as output? Once we get the signal, the signal of what will it perform? So it just opened the one block of carry, of what of half adder. Are we together? Are we together? But practically, don't think that you just have 2 gates and then you wait the miracles. You just give the binary inputs and you wait the sum and carry. No, 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 no. Without power, they will never work. This is figure what? Samandito. Figure what? Samandito is not in the class. Figure 2. The schematic circuit diagram. The schematic logical circuit diagram of half adder. But this is just the block of half adder itself. Why didn't you show the power supply, the input source, the carry, the sum? Because according to this systematic symbol, we just use only 3 pins of these logic gates. While the physical logic gates, integrated circuits, are not, or they don't have 3 pins. They have more than 3 pins, and some of the pins are used to power the integrated circuit. Class, are we together? Are we together? Uh-huh. Get it? Okay. So if this is the case, this is all about the theoretical concept. What do you think if you want to implement in the physical environment? How can you implement that half adder? Come. Urasas, neighbor, come. Urasas, neighbor, come. Come with your stuff. Quickly. So, now let us discuss about, I said come, hardware implementation of half adder. Sit there. Sit there. The second row on that side. How can you implement and verify the performance of the half adder in the hardware environment? Skip some spaces and write, see what are the space that you have been slumbering and get in touch. Okay. So he said that to implement the combinational logic circuit of half adder require the DC power source, the bit or the input bit generator or source, and the sum and carry lots or indicators. So the block of input unit might consist either a digital sensor or bit generator or pull-up resistor network or pull-down resistor network. So you say the block of input unit may consist one of the following sources of binary bits. It can be either a digital sensor, say digital sensor, say digital sensor, or it can be a bit generator, say bit generator, or it can be a pull-up resistor network, or it can be a pull-down resistor network. So you can also have some other sources, number 5, number 6, number 7. These are just some of them. So to simplify the concept, let us use getting. You don't know how to say thank you, eh? Huh? So let us simplify the concepts by just using the pull-down resistor network. So in this case, we will implement the schematic half adder circuit diagram, half adder circuit diagram by using the pull down resistor network. Say pull down resistor network.
Pull down resistor network.
Joseph Pasco, what are you doing with my attendance? Answer the question. What are you doing with my attendance? You're doing nothing while you have it. Do you want to edit? Okay. So, it's your assignment to go and learn how digital sensors can be used as the bit generator or as the source, or how can you connect them with the half adder, half adder circuit? How can you use bit generator? How can you use pull-up resistor network? But because I need, it means that we are going to use the pull-down resistor network or pull-up resistor network as the digital inputs in the concepts of the half adder and full adder, also in the concepts of the encoder and decoder. That's why I have to teach you in advance, because we need this one. And we'll do it practically. And we'll see the pull-down resistor network or the pull-up resistor network. It depends on your efforts. So the pull-down resistor network is just nothing. Say pull-down resistor network. The pull down, okay. The pull down resistor network. So the pull down resistor network consisting, the pull down resistor network consisting, we say that this is the network, say that is a network that consisting a pull down resistor and a push button. Push the button with DC power source. So we are going to have a DC power source, which we call TVCC, or we call TVDD, depends where are you going to use, because you use this pull-down resistor network in most of the digital circuits, including microcontroller, including microprocessor, including logic gates, including sequential circuits. So it's very important. And then another components, electronic components, is what? Resistor. Then this is ground. So VCC or VDD. So this is push button. And this is We call it pull down. Pull down resistor. So this is all. So for this case, we need to know the voltage across the push button, and also we need to know the voltage across resistor. So these are the only two testing points. So this is testing point A, and this is testing point B. Are we together? Are we together? So the input that will be fed to our half adder, we are going to draw it here. So this will be our digital input. And this digital inputs always, it will be voltage across pull down resistor. Class, is it clear? Let me just end this workshop by just explaining in brief about the pull-up resistor network. We end the workshop, then we meet for the next workshop. And there's a sequence of workshops that will be coming. I think that for the digital electronics communication circuit, we still have more than 7 workshops, or I think 7 to 8 workshops. So they are still coming. So, stop writing. Stop writing. When somebody asks you in a simple language, what is pull down resistor network? Simple. Pull down resistor network, this is the network that consists just 3 components. Pull down resistor, push button in most of the cases, and DC power source. Right? And I drew this the schematic circuit diagram. So this the schematic circuit diagram. This the schematic circuit diagram of pull down resistor network. Pull down resistor what? Network. Pull down resistor network. So with this schematic circuit diagram, I said stop writing. This one and this one represent the DC power source. Are we together? Are we together? This one, or this symbol and this symbol represent the DC power source. Say DC power source. And then the second component of the pull down resistor network is just what? A push button. This is the push button. Yes, ka? Yes, ka? Yes, ka? And then the third components, we say it is what? Pull down resistor. So this we call it pull down. Why it's called the pull down? Because it's pulling power towards the ground. Okay? Okay? So it means this push button will be operating in only 2 states. When it's not pressed, then it's giving 1 digital state. When it is pressed, then it's giving another digital state. That's why we have used it. Again, I told you that. Where are we going to draw our input signal? So the output of this pull down resistor is drawn between the push button and resistor. Are we together? So this is what we are going to feed into the half adder. How are we going to feed? Remember that the sum of the half adder, we say that we are going to use exclusive OR gate. So what we are going to draw from here, we are going to connect here. I know you are expert in theories of digital electronics, but you are not expert in practical. So you don't think about how can you illustrate that concept practically. The fifth one, we have also something called a logic toggle. Logic toggle also, toggle can also act as what? As the binary, or as a source of the digital bits. So remember that the principle that we are using for this pull down resistor. It's what? Potential divider. Say potential divider. Say potential divider. Once you remember the potential divider, you can know the theoretical value that you're expected to measure at this point when the push button is pressed and when the push button is not pressed. So what will be the output voltage? Well, you know that it's resistance of the push button divided by resistance of the push button plus resistor. Then multiply by what? VCC. Right? Right? Johan, are you there? So we expected two results. The first result when the push button is pressed. The second result when the push button is not pressed. Okay? Then, how can we calculate the voltage across this resistor? Well, potential divider. We have a resistor over resistor plus resistor of the push button multiplied by VCC. Are we together? So also here you expect it to have two values. When the push button pressed and when the push button is not pressed. So simply we expect to have four numbers. Two numbers, theoretically. And then so you have to use the voltmeter to verify. Class, are we together? So in this workshop we have discussed just two blocks. We are not going to discuss about the power supply units because I have taught you. So we still have a discussion about how we are going to implement the sum and the carry of the half adder. So we discussed the half adder itself, we discussed its input. Hopefully in previous workshop we discussed the DC power supply unit. So we just have two simple discussion, and then I will draw the overall schematic hardware, schematic circuit diagrams of half adder in hardware implementation. Means if you want to build it in the breadboard, so if you want to build it in Vero board, or if you want to build in PCB board, how are you going to verify? Or how are you going to test it? Or how are you going to implement? Class, are we together? Is it clear? Okay, any question about what we have discussed? Okay, I would like to say that this is the end of second workshop for the digital electronics communication circuit. I would like to invite you in the next workshop where actually that we'll have workshop 3. We are going to discuss about the block of sum, the block of carry of the half adder, and then we'll enjoy something very important to test our understanding. I would like to insist students, all the students, to make sure that to go through all of this material before we dive into the study workshop, because we'll need also some key concepts in the next workshop. So thank you very much. Welcome to the next workshop. Be blessed. Bye-bye.
Mungu ibariki Tanzania. Nekiny.